Hello everyone, today we are going to learn topological sort because it is one of the most important topics in DFS interview questions. So what is a topological sort? Well, it is a linear ordering, or you can also call it a sequence of nodes, and in this ordering the node u will be written before the node v if there is an edge between u and v like this. So it simply means that we will have a graph and we have to write the nodes of this graph in a sequence where the node u and node v, if there is an edge between u and v like this, we will have to write u before v in that sequence or in that ordering. So suppose that we have this particular graph and now we have to find out the topological sort for this graph. There are a few topological sort or topological ordering available for this, and all of those orderings are valid. You can use any of them. All you need is one. So by definition, we notice that if there is an edge between u and v like this, we have to write u before v. It also means that we can write v after u, right? So if I start from the ending node, the leaf node 6, then I can write it like this. So I have 6 here. Then there is an edge from 5 to 6. So I want to write 5 before 6. It means I can simply write 5 here. Then I also have 7. So we have an edge from 5 to 7 like this, right? It means we have to write 7 after 5. So it means I have to write 7 somewhere after 5. Where should I write it? Should I write it after 6 or should I write it before 6? Well, both of them are fine. Both of them are valid ordering. Why? Because 7 and 6, they do not have an edge. So you do not need to worry about in which order you want to write 7 and 6. You can write 7 and 6. You can write 6 and 7. So I write 6 and 7 here. So I have 5, 6 and 7 at this point. And now that we have written 5, it means that we have gone through this entire part of the graph, right? It means I need to figure out the fourth. So what are the other nodes that have an edge to 5? Well, we only have 4, right? So we have to write this node before 5. Because we have an edge like this. So we can simply write 4. Similarly, we can write 3 here. Then we can write 2 here. Then we can write 1 here. So this particular ordering is a topological ordering or a topological sort. We also have another topological sorting for this graph. 1, 2, 3, 4, 5, 7, 6. So in these two sorting, the only difference is the order of 7 and 6. Here we have 7 and 6. Here we have 6 and 7. The reason we could interchange these two numbers is because there is no edge between 6 and 7 directly. This edge does not exist. So it doesn't matter in which order we write them. So here we started from the ending node, the leaf nodes. But if I start from the first node, what will happen? Well, I will simply write 1. Then I will see if there is an edge like this between 1 and any other node. Yes, we have 2. So we will simply write 2 after it because the node u needs to be before v. So here the u is 1. And then the edge is like this, and then the v is 2. So we are on the right track, 1 and 2. Then from here, the u is 2 and the v is 3. So we are going to write 3 here. Similarly, we will write 4 here. Similarly, we will write 5 here. And then we have 5 as the u, and we have 2 v's. One is this and one is this. So we can write 6 here and then 7, or we can write 7 and then 6. It is completely our choice. So this is also a way for you to figure out the topological sorting. Of course, currently we are using our eyes to figure out these sortings, and we cannot do that in very complicated graphs, and so we will have some algorithm for them. But this is a very rudimentary way for you to figure out, okay, this is going to be the topological sorting for this particular graph. One thing to keep in mind is that topological sortings exist only for DAGs, which means directed acyclic graph. So why does it not exist for normal graph? If I have a graph like 1, 2, then 3, then why can I not figure out the topological ordering for this particular graph? It is an undirected graph. We do not have these kind of arrows, right? So why can I not figure out the topological sorting for an undirected graph? And the reason is because any edge here does not represent a one-way connection. For example, here we have an edge from 1 to 2, right? But what this really means is that we have an edge like this, 1 to 2, and we have another edge like this, 2 to 1. We are simply representing these two edges with the help of a single edge, and we are removing arrows to say that, okay, we have a two-way connection. We can go from 1 to 2 and 2 to 1. But here's the issue, right? If I can go from 1 to 2 and 2 to 1, how can I write an ordering for these two nodes? Suppose that we don't even have the third node. What about these two nodes? Can I write topological sorting for these two? I cannot, right? Because if I say that this is u and this is v, and we only look at this particular edge, we will end up writing 1 before 2, right? But there is also this edge, right? It means we need to consider this edge also. So because of this particular edge, we will have to say 2 needs to come before 1. Because for this particular edge, 2 will become u and 1 will become v, right? And this is the issue that we are facing. We are not able to figure out whether we should write 1 before 2 or we should write 2 before 1. Because we actually have two edges here, right? It's not a single edge. And that is why we are not able to write topological sorting for undirected graphs. But why the acyclic graphs? Suppose that we have this graph, we have an edge from 1 to 2, and then we have an edge from 2 to 3. So if I try to write a topological sort for this particular graph, it will look like this: 1, 2, 3, because we have u, then v, and then we have this particular edge, right? So u is appearing before v, and then for this particular node, this is the u, this is the v. So here also the u is appearing before the v. So it is okay, it's a perfectly valid topological sorting. What if I have an edge from 3 to 1? Like this, then what will happen? Well, if I start from the 1, then till reaching 3, we will get this particular topological sorting. Till now, everything is fine. But as soon as I reach 3, and I say that 3 is the u now, and 1 is going to be the v again, and this will be the edge, now I have a problem, right? The u, that means the 3 should actually exist or written before 1. But if I try to do this, then it will become like this. Then we have this particular 1 duplicated, but we don't have 2 nodes as 1. We only have a single node. So how can we write this particular sequence? Because I end up creating a duplicate here. And this is not a valid ordering, right? Because we only have 3 nodes, we don't have 4 nodes, right? And so it means here also we are facing the same issue, whether we should write 1 before 3 based on this implicit edge. So whether we should use this and write 1 before 3 like we have here, we have 1 here and 3 here, or we should use this edge and write 3 before 1. And so we end up in the same situation again, not able to decide whether we should write 1 before 3 or 3 before 1. And that is the reason why we do not have any topological sorting for cyclic graphs also. And that is why we are saying that the topological sorting exists only on DAG, Directed Acyclic Graphs, the graph that have nodes and then edges like these directed, and they do not have any cycles. Only for them we can figure out any topological sorting. Otherwise, in every other case, we will have this particular situation repeat again and again somehow, and we will not be able to create a topological sorting for those other cases. Now, here is a big question. Since the topological sorting is very important, what exactly is the use of it? Why are we even trying to create a topological sorting for a graph? Well, it is really useful, guys. Suppose you are actually working in a big company. Okay, in that company, you are having a big project, and that project is divided into components. Component A, right? Component B, then we have component C, then we have component D, like this. Okay, then we suppose have a component E. Now all of these components are basically created by different teams. So different teams are working on this component, but that does not matter here. Okay, so you have the components. Now suppose that D is actually the base component. This is the component that is actually going to provide facilities or functions or libraries to other components, so that other components will not have to create their own functions. They can simply use the common functions from the D component. What this means is that there will be an edge from D to C, then D to B, and let us make an edge from D to E also. So it means that these three components E, B and C are using functions or libraries created in the D. And then we have the A. So A is taking some stuff from E, then A is taking some stuff from C, then A is also taking some things from B, and then eventually we get a product that something user can use. So we have been able to create this particular graph. It is called the dependency graph for components because C depends on D and then A depends on C, right? So when you will try to place your application on production, you will have to build this particular application. Building simply means taking all the code that is present in these components and converting all that code into platform specific code or machine code like 001 or something like that. You might end up creating something like byte code in case of Java, but that doesn't matter. Eventually, you will have to take all these components and build them into some kind of file. So when you are trying to build these components, then it will become very important for you to figure out which component to build first, right? Because you cannot build C until you build D, because C uses functions from the D. It means if you try to build C before D, you will get an error that the function from the D does not exist. So it means the first thing you need to build is D, then only you can build E, C and B, and then only you can go ahead and build A. If you try to build A first, you will get the error that E does not exist, C does not exist, or B does not exist. And so what this means that there is a particular ordering or a particular sequence in which the component needs to be built. First, we need to build the D. Then we can go ahead and build E, C, and B in any ordering that we want to build them. And then only we can go ahead and build A at the last. And this particular ordering or sequence is basically the topological sorting. So it means these are the kind of places where we actually use topological sorting. We will have to first build D. So D will come first here. Then we can build ECB or BCE or CBE in any order. So I will say ECB is my choice. And then only I can go ahead and build A. So this is one of the linear orderings That is the topological sort. There can be other ordering also. If I try to build D first, and then I can build C, B or E, and then in the end I build A. This is also a valid ordering. So this is the place where we actually use topological sorting, and there are hundreds of other use cases where you can use topological sorting. Now one more thing is that suppose I have a dependency from E to D, and this is the kind of cyclic dependency that we do not want in production code ever, because it makes it impossible to build this production application. We will have to figure out some workaround through this particular dependency. So since we are dealing with graphs, there will be two ways to figure out the topological sorting. One is DFS and then we have BFS. We are going to look at the DFS here first. So suppose that we have a graph like this. Now we want to figure out the topological sorting for it. The first thing that we can do is we can take all of the leaf nodes in the graph and take them and place them in the sorting order. We have 4 here. Then we can go backwards. So from 4 we can reach 3. And so I will simply write 3. Then I have two options. I can go 1 or I can go 2. It means I can simply write anything like 1 or 2 or 1. It's my choice. And then from here we have this particular node, right? 0. So 0 needs to come before both 1 and 2. So 0 will be here. So in this approach, we actually took the last node, the last leaf nodes, and then started from there, just backtracking from there, right? And so that is exactly what we can do with the help of DFS also. So here is the DFS algorithm that we can use to find out the topological sorting for any graph that we want. So in the DFS, first of all, we are taking the node and we have a visited array. If you do not understand how DFS works, please watch my other video in which I am explaining DFS. That is a prerequisite for this video. This visited set contains all the nodes that we have already gone through. Now inside of the function, first of all, we are marking this particular node as visited so that we will not go to this particular node through any other particular node and edge ever again. And once we have marked it true, we will use a for loop to go through all the neighbors for this particular node in the adjacency list. So we will take all the neighbors for this node in the adjacency list and we will check if that particular neighbor has not visited. If it is not visited, then we will run the DFS on this particular neighbor also. But if it is visited, we will simply skip it. And at the end, after the entire for loop completes, we will simply take the current node, this one, and place it inside of a stack. So it means we will have a stack like this. Now, if I try to use this particular function on this graph, what will happen? Well, I will start from 0. Suppose I will be on DFS of 0. So D of 0, we have started here. Now I will mark it true in the visited set, and then I will go through all of its neighbor nodes. So neighbor is 1 and 2. Then I will just take any direction. Suppose I take the direction of 1. So I will go here and I will have DFS of 1. Now I will mark this 1 true and then I will go to the next node. The neighbor of 1 is 3, right? Then I will go in this direction. I will have a DFS of 3 and then I will mark this also as true in the DFS function. And then we will go to the next neighbor, that is 4. Then I will have this DFS of 4 and here I will mark it true. Then I will use the for loop to go through all of its neighbors, but I will realize that it does not have any neighbors, right? There is no outgoing edge from 4 to any other node. It does not exist. It means it is a leaf node. So this for loop will simply exit because this adjacency of nodes will be empty. And once it is exited, we will use this particular line stack.append and we will append the node 4 inside of the stack. So we will have 4 here. Then we will end up going back from D of 4 to D of 3, right? And now we will try to see if there is any other node connected to 3. Well, we do not have any outgoing edges. We do have an incoming edge from 2 to 3, but that is not an outgoing edge. We do not consider that. We only consider the outgoing edges. There are no other outgoing edges, so it means that this for loop that was running in the call of DFS3 will also end and we will reach this particular line, the stack.append node, and we will append 3 also in the stack. Then we will go back to the 1. We will come back here on DFS of 1 and here we see that there are no outgoing edges anymore. That means the for loop for 1 will also end at this point and we will reach this stack line. We will end up adding 1 in the stack. Then we will go back to the 0 and we will try to see if there is any other outgoing edge. We have an edge from 0 to 2. So we will go for DFS of 2 now. Now here also, first of all, we will mark it visited inside of this visited array. Then we will see the for loop. We will try to go through all the neighbor nodes for this 2 node. We will see that there is one neighbor, that is 3. But we will check if the visited of 3 is true or not. If it is true, we cannot go inside of it, right? It will be true here. Visited of 3 will be true. We cannot go inside of it. And that means we will try to go to some other neighboring node. But 2 does not have any other outgoing edges, right? 3 was the only one. So it means the for loop will end at this point and we will reach the stack line. We will append this particular node 2 in the stack again. So we will have this particular node 2 here. and then we will go back from 2 to 0, right? And then here on DFS of 0, we will try to see if there is any other neighboring node available for 0. There is no neighboring node available now, so the for loop will end for 0 also, and then we will reach this stack line for 0 also. We will append the 0 in the stack. So it means we have 0, 2, 1, 3 and 4 in the stack, and now I can just start taking them out. I will take out first of all 0, then I will take out 2, then I will take out 1, then I will take out 3, then I will take out 4. And this is the perfect topological ordering for this graph. It is actually one of the topological ordering because you can interchange these 2 and 1. So you can have 0, 2, 1, or you can have 0, 1, 2. That is up to you. Why? Because we got 2 inside of our topological sorting because we decided to go from 0 to 1 first, and then we went from 0 to 2 afterwards. Otherwise, we would have got this thing 0, 1, 2, 3, 4. So what we are doing in the DFS algorithm is very simple. We are going through the node, we are marking it visited, we are going through all of its neighbors and then running DFS on them if possible, and at the end of the day we are taking the current node and appending it into the stack. That's it. There are only 3 steps: mark it visited, go through the neighbors and append it into the stack. That's it. And the intuition behind this algorithm is something that we have already discussed. In our earlier discussion, when we were discussing about what is the topological sorting, we tried to find the topological sorting from the leaf nodes, right? We just started from the leaf nodes and then we went backwards, right? We wrote the 6. Then we see that there is an edge from 5 to 6. So we will use this as U, use this as V. We will write U before V. So we will have 5 here. Then we also see that we have 7 here. So 7 and 6 does not have an edge. So I can write 6, 7 here or 7, 6 here. Depends on where I started from. If I would have started from 7, I would have wrote 7, 6. But now here we are on 5. It means this entire graph is done. Now we have U as 4, right? And 5 as V. So U must come before V, right? So we will write 4 here. Similarly, this will become V. This will become U. We will have 3 here. Similarly, this will become V. This will become U. We will have 2 here. Then this will be V, this will be U, we will have 1 here. So the same intuition is exactly what we are using in the above DFS function. We are going for the leaf nodes and we are starting from there. We are going till the leaf nodes and then we are appending the leaf node in the stack, and then only we go back and append other nodes. That's why we have first of all 4, then 3, then 1, then 2, then 0. And when we take them out, we actually get this particular topological sorting. Here is the more formal code in Python. We have the DFS for topological sorting function here. It is taking graph, then it is taking the start node, it is taking the visited set or visited array, and it is also taking the stack. You can use them as global variables also, but I'm just placing them inside of the function so that it will be easier to access them. Then the first thing that we are doing is marking the start node or this particular node visited. Then we are going through all of its neighbors with the help of this graph adjacency list. So for neighbor in the neighbor of this particular node start, we go through the neighbor, we try to run DFS on them if they are not in visited. If they are in visited, we do not run the DFS, we simply move on to the next neighbor. And once we have gone through all of the neighbors, we will simply append this node into the stack. Simple, right? The same 3 steps that we already discussed. Now you can use this function for the connected graph, where every node is connected to other node in some way. But there can be graph where nodes are actually isolated. There can be groups of connected nodes. We call them connected component. What will you do in that case? Well, here is what you will do. So in the execution part of the code, we are creating the visited set, we are initializing it, then we have the stack, we are initializing the stack also. And here in this part, we are going through each and every node of the graph. So if the graph has like 5 nodes, we are going through 5 nodes. If the graph has 100 nodes, we are going through 100 nodes. If the graph has n nodes, we are going through n nodes. And here we are trying to see if the node is already visited or not. If it is not in the visited, we will run the DFS topological sorting algorithm on that node also. This particular code will help you go through all of the connected components inside of a graph. It means you will always have the perfect linear ordering or the perfect topological sorting for any kind of directed acyclic graph. Whether it is connected or not connected does not matter. And here in the end line, we are simply printing the topological sorting. Here you can do whatever you want to do with the sorting. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.